Hi friends, let's start with equipotential surfaces. All those surfaces which have equal potential on all the points of the surface, they are known as equipotential surfaces. And for a small positive charge, you know that potential is given by V is equal to kq by r. Now, here I know that k is a constant and q is fixed. So, if r is constant here, then my potential will be constant. So, uh, if I take a sphere which is centered at this positive charge, then for all the points on the sphere, my r is fixed. So on all the points of the sphere, my potential is constant, which is kq by r. So for a positive charge, for a point charge, uh, a sphere which is centered at the charge itself is the equipotential surface. And take another example. If you have a constant electric field, then any surface which passes through the electric field and is perpendicular to the electric field, you can call all these rectangles as equipotential surfaces. And observe a common property in these two examples. You see that electric field lines uh, get out or protrude out normally out of the surfaces, or I should say the area vector of this equipotential surface is parallel to the electric field lines at every point. Observe here, this is the electric field direction and this is the area vector of this surface, of this equipotential surface. Actually, this is a property for any charge configuration. Equipotential surface through a point is normal to the electric field at that point. And let me prove this. If actually say this were not parallel, the area vector and electric field were not parallel. This is the area vector. If I had some electric field in this direction, what it means? It means that I have some tangential component, or I should say I have some component of this electric field which is in this direction parallel to the area. So this means that if I place any charge on this surface, because of this electric field or the tangential component of this electric field, there is a movement in this charge. But that shouldn't happen because there is no potential difference between any two points on this equipotential surface. So the charges should be at rest. Of course, the charges move only when electricity passes through the surface or conductor, whatever it is. That's a different story. But here, since the charges shouldn't move, or I should say, since all the points on this surface have equal potential, this is possible only when there is no component of electric field on this surface, and in turn that means that electric field is perpendicular to the surface at all the points. Now let me give some other examples. When you have a dipole, I mean two opposite charges of equal magnitude, then these are the surfaces. All you see, the center line which you see in the middle of the screen vertically, even that is a surface. That is an infinite surface. Even that's an equipotential surface. And this is the example for two opposite charges of equal magnitude. And note here also that the electric field lines are perpendicular to the equipotential surface at every point. Just observe that. And this will be the example for two charges of equal magnitude and equal sign as well. All the dotted lines which you see are the equipotential surfaces. Have you ever observed this? Just try to observe the formulas of electric field and potential. Both of them are pretty much similar. They just differ by the denominator. Here it is r square and here it is r. So have you ever felt that when we divide the potential by something which has a unit of length, you may end up with the electric field? In fact, that is true. I'm going to explain you that. Take two equipotential surfaces, and I'm assuming the first surface to be at higher potential. Let this be V plus dV, and let the potential of this surface be V. Let the distance between these two be dl. Of course, there will be an electric field. Now, I want to take a positive charge from this first surface to the second surface. The work done will be electric field into this length dl, which will be equal to of course, I'm trying to take a unit positive charge. So this will be equal to the difference in this potentials, which is nothing but V minus V plus dV. That's nothing but minus dV. Now why is this minus? dV is positive, I know that, because I assume this to be in higher potential state. So this minus indicates that the work is negative. I mean, I don't have to do any work, I'll get work, because charge always tries to get into a state of lower potential than higher potential. So forget all these signs. Simply I can say that at least this magnitude of electric field is equal to the magnitude of change in potential divided by the distance. Now this is what I'm going to say. This is actually a property. Magnitude of electric field is the change in magnitude of potential per unit displacement, which is normal to the equipotential surface, of course. And the direction, what about the direction? The electric field points in the direction in which the potential decreases the most, I should say. And let's move forward. Potential energy. Potential energy is nothing but the energy which I need to do to bring the charge to the state which it is present at the current moment. Or see the definition. I'll explain some important terms. Potential energy of a charge q at a point in the presence of any external electric field is the work done by external force, that's me. And see this, equal and opposite to the external force. Why is this? As I said before, it's not enough if you bring the charge. It's mandatory that you should bring the charge very slowly. The charge shouldn't accelerate. It's only possible when your external force is equal and opposite to the electrical force. And you're bringing the charge from infinity to that point, because the convention says that the potential is 0 at infinity. That means that the potential energy is also 0 at infinity. That's why you have to bring it from infinity to the required point. Now say I don't have anything in the universe except one charge, so I don't have any influence on this charge. So to bring this charge to this point, I don't have to do any work. Now if I want to bring another charge to this point, now I have the effect of this q1 on this charge. So the potential at this point before bringing it here was 1 by 4 pi epsilon naught q1 by let the distance between these two be r12. So this was the potential here at the second point. Now I wanted to bring the charge q2 from infinity to this point. So the work I had to do is this potential at this point into the charge which I'm bringing. So this is the work, or this is the potential energy. This is the work I had to do, and this gets stored as the potential energy. This is for two charges, right? So when we are dealing with three charges, here is one charge q1, here is another charge q2. Now if I want to bring another charge q3 here, I have to multiply this charge q3 with the potential present at this point C before I bought this charge. So the potential before was 1 by 4 pi epsilon naught q1 by r13, which is the distance between charge q1 and q3, plus q2 by r23, which is the distance between charge 2 and charge 3. So this was the potential before bringing the charge 3, or this is the potential experienced by charge 3 by charge q1 and q2. Now I am going to multiply this charge q3 with this potential. I'll get the work done by q3 on q1 and q2. So similarly, before itself I had to do some work to bring charge q2. I mentioned it here. It is something this, and for bringing q1 I didn't have to do any work. So finally the net potential energy of my system is the 1 by 4 pi epsilon naught q1 q2 by r12 plus this thing, this whole thing. This is the potential energy of my system. See, potential energy is the characteristic of the present state or configuration, and so it doesn't matter how you bring the charges. I mean, the answer would have been the same even if you bought Q3 first, Q2 next, and Q1 at the last. Finally, if these three charges are present in this state, to make this happen, you'll have to spend the same amount of energy, irrespective of the order in which you bring these charges. Let me write it for you. The potential energy of the system becomes into Q1 Q2 by R12 plus and there are three charges altogether, and 3C2 is 3, so there are three terms finally. Let's move further. Here's the problem. This ABCD which you are seeing is a square of say side D, and as you see, A and C have positive charges and B and D have negative charges, all are of same magnitude. Now what is the potential energy of this system? So let's do it stepwise. First, I'll bring a positive charge plus Q to the point A. For that, I don't need any energy because no effect, no influence, no electrical environment was present before. Next, I'll bring negative charge minus Q to the point B. For this, I'll have to do a work of this negative charge Q into the potential which was there at this point B, that is Q by 4 pi epsilon naught D. So this is the work I had to do to bring charge B. Now let me bring charge C now. So this work will be the charge C into the potential which was present at the point C before bringing charge C. That will be 1 by 4 pi epsilon naught Q by D root 2, which is the distance between A and C. This term is for potential due to charge A, and you have minus Q by 4 pi epsilon naught and D. This is due to charge B, and you also have the work done due to D as charge D into the potential which was present at D due to all these three charges, which is nothing but Q by 4 pi epsilon naught D due to A, and minus Q by 4 pi epsilon naught D root 2 due to B, and Q by 4 pi epsilon naught D due to charge C. Now I should just add all these terms A, B, C, D to get the net potential energy of this system. That's just maths. You just do it. You will get something like 4 minus root 2 into minus Q square by 4 pi epsilon naught D. Now this is the potential energy of the system. I started with A and ended with D. You don't have to do it the same way because potential energy is just the characteristic of a system. So you can start with D and end with A as well. Hope everything is clear till now. Now let me tell you something more interesting. What if I want to bring a small positive charge Q naught at this point, which is at the center of this square? After assembling all these four charges, I'll calculate the potential at the center due to all these four charges, which is nothing but 0. Observe this. All the charges are of equal magnitude, and 2 of them are negative and 2 of them are positive, and all of them are at the same distance from this center because that is center, and hence the net potential, if you calculate, will be 0. So you don't have to do any work to bring any charge to the center of this square, and that's it for today. In the next video, I'll be talking how to calculate the potential energy in external field and some other stuff, and keep watching. That's it.